Thank you. Thank you. Good afternoon. My name is CLYDE ABELA. I'm the Associate Director at WINTECH. And I'm going to talk about something less visually interesting. It's hard to follow on such an interesting presentation. It's also going to be a bit more technically heavy, so I'm hoping you're ready for that. Here we go. A bit of background on WINTECH. WINTECH is a facade consultancy firm, has been working purely on facades for the last 35 years, and we've got our main office in the UK, and we've got a Middle East and USA office, as well as dedicated independent testing based in Telford in the UK. So residential, I'm going to talk about mid to high rise. So it's where we find challenging designs, where we've got non-standard building designs. We have difficulties in including fixed glazing, but also sliding doors and operable vents into the facade, complex junctions such as balconies, and then the usual fire safety, higher acoustic requirements, accessibility, and so on and so forth. And on top of that, tight budgets and tight program. Very quickly, the regulations requirements to meet Part L, 5 criteria. The last 2 are not really relevant for performance perspective. It's making sure that the requirements are actually implemented and making sure the users are educated accordingly. The first 3 criteria are related to facades and many other aspects of the building, but obviously we're going to talk about the facade, and especially the target fabric energy efficiency. The SAP 2012 methodology, which is what is used to assess thermal performance in buildings, has a set of prescribed figures which you can or decide to apply. Today, I'd like to focus purely on thermal bridging, wall U values, and how to also incorporate curtain walling. To talk about that, we need to talk about thermal bridges generally. We've got 2 types as defined in the building regulations. There's repeating and non-repeating thermal bridging. Repeating thermal bridging is the sort of thing you'd find in lightweight wall construction, things like stud work, brick ties, mortar within the brick, and brackets through insulation in lightweight metal construction like halter brackets or rain screen brackets. And the way you'd go about that is you'd normally take a typical rain screen bracket, you'd model it in 3 dimensions, including all the fixing methods and metal elements, apply a temperature difference, and you can calculate the heat loss through that element. You can also look at other things like where the dew point would sit in a particular condition and whether you've got risks of condensation, whether you need to address that in some other means. Based on that, we've done quite a few research within our company to try and make it easy for us to give early advice on what sort of performance you'd expect from a rain screen and from other similar details. The blue line is what we'd normally expect on a typical building nowadays. It's an aluminum thermally broken bracket. And for different U values you might want to hit, you need different thicknesses of insulation. And generally we're talking about mineral wool non-combustible insulation in this situation. So, for example, if we wanted a U value of 0.18, which is the default notional figure, you'd be looking at around 2 to 225 mil of mineral wool insulation. Change that to a stainless steel bracket and you go down to the bottom curve and you can reduce your insulation quite significantly, 140 mil, at quite an increased cost. There's also the spacing to take into account. You can try to work with that. 600 mil is what has been assumed for these curves, vertically and horizontally. Generally, if you have an uninterrupted wall, you might be able to do much better than that. But when you start putting windows around in rain screen openings, you end up with rails with an average of 600 mil in our experience. So that's repeating done. Non-repeating thermal bridging are more complex junctions which occur less frequently, and there's typically walls interfacing with windows and walls interfacing with slabs and the like. And you get things like brackets to support brickwork and different types of them, but also balcony connections and terraces and so on. So how does Part L deal with this? There's a number of ways, but in principle, you've got a notional building and your own design reference building, and you model it twice, once based on the notional figures, which is what we've seen in the previous slides, and one with actual performances which you are going to apply to your own buildings. Now, in the past, the easy way of doing it would be to use a Y value of 0.15. This requires no evidence of compliance. It's just a fudge factor in a sense, and you'd be allowed to get away with not having to look into non-repeating thermal bridges in lots of detail. This loophole is being addressed with the new SAP 10, which is still to be released for use. the standard default Y value will be increased, so your design would be more penalized than it ever was for not taking into account non-repeating terminages. The other option is to use default figures or accredited details. Default figures, again, are quite onerous. Accredited details generally tend not to apply to the designs we're looking at because they're also bespoke. So you're left with the last option, which is to actually calculate it. And that is obviously the best solution from a building physics perspective, but it's also the most critical from a procurement perspective because we need to make sure that the details designed at initial stages can actually meet the lower U values, psi values in this case, which we're after. These are the notional figures on the left versus the SAP defaults on the right, which one would apply to the junctions under different conditions. So the notional is the base case, what we're trying to match or improve on. And as you can see, the figures are pretty low, typically half the defaults, with a couple of exceptions, the window lintels and the balconies, which we'll discuss in a minute. BRE has also a number of certified detail, and although they might not be readily applicable to the details we've got on the project, they might provide an idea of what performance you might expect out of your detail. Specifically on window lintels and balconies, lintels, the difference is enormous. There's a 20-fold increase or penalty in heat loss if you don't calculate this junction, and it increases even further for balconies. The good thing is with lintels, we know we can actually achieve much better than 1, and generally we can meet or improve on the notional figure. It's the balconies which are a bit more troublesome because the notional figure is pretty much impossible to meet. I'm not certain why that's in SAP. We've asked the question. We're still waiting for an answer for that. But the default, again, penalizes you heavily with a psi value of 1, and that's where calculation might come in handy. If we look at a typical gem on a rain screen, there's a lot of variables which affect the psi value, but one of the most important is the window location relative to the insulation line. Locating the window in this particular case in line with the stud work would result in a psi value of 0.07, which is not that bad considering the poorness of the detail. Compared to the standard psi value, which is 0.1, but it's still worse than the notional, which is 0.07. The performance quickly improves as you move the window outwards, and it almost goes down to 0, where there's a point where if you move it further out, you start getting a loss because you've got heat bypassing the insulation. Thermally broken concrete balconies, again, there's scope for improvement, but in this particular case, you can't really match the notional figure even if you use the best available products on the market. You might get close if you insulate the balcony, but you'd get very limited benefit out of that. The most complicated junctions on normal residential facades, bolt-on balconies, require a lot of analysis. Large 3D models need to be built, and they are computationally intense and take a long time to analyze due to their size. In this particular case, this particular detail achieves 0.2, which is worse than the concrete balcony, and that's because we also need to consider things like brick supports, which are, again, very heavy stainless steel brackets, which are there to support the brickwork, but form part of the junction and need to be assessed as well. Curtain walling, very difficult, is also a bit of an animal in its own right. The vision glazing notional figure is 1.5. It's a bit higher than windows, and that's because the regulations take into account the fact that this area of curtain wall includes the jamb and interfaces around it as part of the U values. But the opaque areas are at 0.18, which we know is a figure which is very difficult to meet when we're looking at unitized curtain wall. We're looking normally at 0.5 to 0.8, which is 3 to 4 times higher than the notional figure. So you might be looking at triple glazing to compensate for that in your glazing area, or more normally what tends to happen is insulation is added onto the back of unitized curtain walling, and that has repercussions as we're going to see. If we look at a typical unitized facade, some of you may recognize the profiles there. You've got a unitized panel and the insulation marked in yellow there, and then an internal plasterboard lining of some description which is installed later by others. When you analyze that detail, you see that the dew point temperature, depending which standard you use, falls within the unit, and that's more or less what you want. It's outside of your airtightness line. It will hopefully stop any vapor getting into that point and any condensation actually forming. And even if it does, normally the panels are designed with nominal ventilation and drainage so that if there is any condensation, it will evaporate off. Adding 50 mil, and often it's much more than that, on the inside of a unitized panel starts to cause a bit of a problem because it changes the way the facade starts to act. The dew point now goes on the inside, no matter what standard you utilize, and it's on the inside of your airtightness line, and what you will eventually need is a vapor control layer on the innermost face of the insulation. Now this is, you can run a piece of software and with that model, and it will tell you won't get any condensation. The problem is you were trying to create a pocket of airtightness, an airtight pocket within that 50 mil insulation to make sure there's no condensation forming there. And we know the only other airtight pocket we know of in facades is double glazed units, and we know how long they last, considering they are made in a factory and completely sealed off. And in extreme instances, you've got water accumulation within the units, which is unlikely to happen in that scenario, but you have also to consider the workmanship we see regularly with these vapor control layers, partly because of the difficult junctions that need to be dealt with around openings, and partly because it's generally a different subcontractor which has no incentive to actually execute the vapor control layer or doesn't understand why it is even there. What alternatives do we have? Unitized facades with better performance are starting to become available. Larger thermal breaks or multiple thermal breaks seem to be an option from some suppliers, not all, but I think it's certainly something that needs to be addressed in the future if we want to keep doing this. The other obvious option is triple glazing, which is something which the UK is very difficult. It's very difficult to explain to clients why you might need it, even though the regulations are constantly changing. And then the last option you've got in terms of U values is to improve your spandrel performance somehow. There's new insulation types which are being introduced on the market. There's, for example, Calostat here, which has an A2 rating, so that we need to see how the outcome of the current review of the regulations in terms of fire goes, because that might still not be enough. But these sort of insulations and things like vacuum panels can help us provide that improvement. So what can we do on top of actually improving the systems is to avoid excess areas of glazing. Not exceeding 25% of the floor area is a good start. Anything beyond that is considered as a wall in SAP, and you have to therefore compensate for that in your U values. Minimize the amount of interfaces where possible. Larger single windows are better than a lot of smaller ones. Correctly locate the glazing relative to the surrounding cladding. Avoid balconies if possible. Not many have this opportunity, but there were a couple of projects where this was an option. Plan for the correct thickness of insulation. Often architects at early stages do not take this into account, and later it causes us difficulties because things like balcony thicknesses or terrace thicknesses are expressed then in the spandrels, and that might affect the architectural appearance of the building. Finally, I think it's important to consider at an early stage the strategy for dealing with term bridging, so making sure responsibilities are clear, are clarified between consultants, subcontractors, and that this is all procured properly to make sure that the outcome intended is achieved. That's all from me. I hope you found this interesting. I'll be around for any questions if you want.
So any questions now for CLYDE?
Good.
That's nice then.
Yeah, thank you.
Thank you very much, CLYDE.